Lecture 8a of Differential Equations and Linear Algebra is, for the most part, about existence and uniqueness theorems for ordinary differential equations. In Lecture 7a, we did talk about existence in terms of implicit solutions and a basic existence theorem. We'll continue talking about that, as well as a new concept of uniqueness of solutions, and we'll introduce the idea of a phased line. We've talked briefly about phase planes and phase spaces before as sort of a basic idea. Now we want to get into details with some examples in the one-dimensional situation of a phase line. You can also see the topics for Lecture 8b, which will be on linear algebra here. But there's a lot to do as usual, so let's get going. Let's start with an existence and uniqueness theorem for pure antiderivative ordinary differential equations, really first-order ordinary differential equations of this form. dy dt equals little f of t. The right-hand side here depends on the independent variable t. If it depended just on y, we would call it an autonomous equation. If it depended on both t and y, we'd call it a mixed equation. Here, where it depends just on t, we call it a pure antiderivative problem. You can solve this equation essentially just by integration. Now, there's a theorem, the second fundamental theorem of calculus, actually some people call it the first fundamental theorem of calculus, that will guarantee the solution of this exists. And in fact, it will also in part guarantee it is unique. Let's get into the details. So we got this right-hand side function, little f. We suppose that it is a continuous function, continuous on a closed interval. This is going to be a t interval on the t-axis from a to b. We're going to define a new function, not f, but a related function, call it phi. This is consistent with the notation we've used for solutions so far. Sub y0 of t. This is going to be a function of t, time, that will solve the differential equation. And by putting a y0 there in this way, it will also satisfy the initial condition that will be that phi sub y0 of a, the left endpoint of the interval, will equal y0, because when we replace t by a here, you get the integral from a to a, which will be 0, plus y0. It will satisfy the initial condition. This is a function of t. For any given value of t, you get a different upper limit for the integral. So you're going to get, in general, different numbers for outputs. You can graph this as a function of t as well. Doesn't mean you can always compute it. Sometimes this integral would have to be approximated with numerical methods. Then we can conclude that this function phi sub y0 of t is in fact differentiable. It's got a derivative, and it satisfies the initial value problem. dy dt equals f of t. It is an antiderivative of little f. And y of a equals y sub 0. When you plug in t equals a into this function, you will get y sub 0. And that's what I say right here. Let me erase this a little bit so you can see the prime better. Phi sub y0 prime of t, the derivative with respect to t, equals little f of t for all t in the interval. And yes, the initial condition is satisfied. Phi sub y0 of a equals y0. The y0 is a subscript just specifying what value we want this function to have when t equals the left endpoint a. All right, this first equation, the one right here, is sometimes written with ddt notation, operator notation. Ddt of this function, there's my phi function right there. With respect to time, we need to differentiate this. The y0 differentiates to 0. Here, I'm just using linearity of the derivative operator to say that's 0 plus the derivative of this integral. And essentially, the second fundamental theorem of calculus, which again, some people call the first fundamental theorem of calculus, says the derivative and the integral sign kind of cancel, leaving you with the integrand function. But you do want to make sure you put a t in there, not a u. This quantity right there needs to match the upper limit of the integral, and it also needs to match the t right there. Okay? That's the basic idea that you can write this theorem. So, the derivative and integral undo each other. They are inverse operations, and it verifies this satisfies this initial value problem. But is it unique? The solution exists, but is it unique? Are there any other solutions? This is not a trivial problem, actually. In general, we'll see for autonomous equations or mixed equations, for example, this is not trivial. We need a heavier duty theorem. Is that a word? Dutier? Heavier duty theorem to verify uniqueness in that general situation, and existence for that matter. It is going to be unique, but why? Here's an argument. Well, it's based on this fact. Any two antiderivatives of the same function over a given interval must differ by a constant. That's something you know from calculus, right? That's why you add the plus c at the end when you do indefinite integrals. It's also based on the fact that the initial condition must also be satisfied. This preceding fact, that's in boldface here, follows from something called the Mean Value Theorem. If you took Calc 1, you should have learned about the Mean Value Theorem for derivatives. I'm not going to get into the details. I'm just saying, you can look it up. This boldface fact is based on that. Let's use it though. Let's go ahead and give an argument. If we assume, oh, here's another Greek letter. Isn't that pretty? Psi. This is not quantum mechanics. Okay, psi is used a lot in quantum mechanics. Psi of t also satisfies the initial value problem over the interval. Can we prove that psi of t must equal phi sub y0 of t? Well, first of all, if it's going to satisfy the differential equation, then when I differentiate it, blue instead, when I differentiate it, I get the right-hand side function, because that, again, is what it means to solve this kind of differential equation. But wait a minute, I already know that's phi sub y0 prime of t by the second fundamental theorem of calculus for all t in the interval. That means, because of the boldface fact here, there must be some constant c, so this is true. Psi of t equals phi of t plus c. What would we want to show to show uniqueness? We'd want to show c is 0. And that's what we do. How do you do that? Plug in the left-hand endpoint, t equals a. Phi of a plus c must equal psi of a, and this is true because of this preceding line. But we know psi of a is y0. We know it satisfies the initial condition. We're assuming it does. But so does phi. And therefore, if you look at the equality between this and this, that must mean c is 0. C is 0, and we can conclude that in fact these two things are equal with a c equal to 0 there. They're the same function for all t in the interval. In other words, the solution is unique over the given interval. Okay? So it can be proved. And I hope you believe that you could do it if you worked out this hard enough even, maybe with some hints here and there. Okay? It's not an easy thing to do proofs, but once you see them, they should make sense. What about existence and uniqueness in general? Like for autonomous equations. And again, I'll remind you, an autonomous equation is one where the right-hand side depends on the dependent variable. And what it means to solve an autonomous equation like this, if phi is a solution, it means phi prime of t equals f of phi of t for all t. You need to replace the y on both sides, really, with phi of t, take its derivative here, replace y with phi of t there. That's what it would mean to solve this kind of autonomous differential equation. That's a point of confusion for many people, so make sure you understand that. And yeah, what about for mixed equations? If we have a mixed equation where the right-hand side function depends on both t and y, we talked about this in lecture 7a, and we made contour maps to help us draw slope fields. That's an important kind of skill here. It would mean phi prime of t equals f of t comma phi of t for all t in some interval again. Plug in phi in both the left and right hand sides in place of y. Here it means take the derivative, here it means replace this y with phi of t. When you simplify both sides as functions of t, you get the same thing. That's what it means to solve those kinds of differential equations. But it's much harder to prove existence and uniqueness for these. The fundamental theorem of calculus, in either form, does not apply really. It's not a pure antiderivative problem. And in fact, solutions themselves are typically impossible to find in closed form using elementary functions. There's typically not a name for the solutions. You could give them names, but maybe nobody would care. If somebody did care, or if lots of people cared, you could maybe even patent your name. You've got your very own function named after yourself. But in general, nobody's got formulas for them. Doesn't mean they don't exist, and it doesn't mean they can't be approximated and understood, but there's just no simple formula for them. Closed form means also that there's no infinite series. This is a non-infinite series thing. That's what we're talking about there when we say closed form. In fact, sometimes f can even be really relatively nice, like continuous everywhere. Yet, for example, uniqueness can actually fail. Continuity will be enough to guarantee existence, but not necessarily uniqueness. Let's look at an example of that. dy dt equals f of y equals y to the 2/3, y of 0 is 0. That's an autonomous differential equation. We're looking for the solution or solutions that go through the origin. What happens when we try to solve this? Let's go ahead and separate variables and see what happens. So, divide both sides by y to the 2/3 to really get y to the negative 2/3 on the left side, and it cancels on the right side. Quote unquote, multiply both sides by dt. Again, that's not what we're really doing, but it doesn't hurt to pretend. We've talked about that. Integrate both sides. Integrating the right side, integrating 1 effectively, gives you t plus some constant, I'll call it c1. Integrating the left-hand side is easy too. You're going to have to add 1 to that exponent to get y to the positive 1/3, and also divide by a positive 1/3, which is the same as multiplying by 3 to get this. The goal is to solve for y. We can do that. Divide both sides by 3 to cancel the 3 on the left there. We'll get a t over 3 and a c1 over 3, which we maybe could call c instead of c1 over 3. Then we want to also cube both sides to get rid of this 1/3 power, and this is what results, where c really is c1 over 3, but these things are arbitrary constants, so I can not worry about writing c1 over 3. All right, now let's use the initial condition. 0 equals y of 0, plug in t equals 0 here, you get 0 over 3 is 0, 0 plus c is c, and we get a c cubed. So c cubed must equal 0, that means c is 0. So, what this evidently means then is y equals 2/3 quantity, let's see if I can write this over here, y equals, or 1/3, excuse me, 1/3 quantity, 1/3 t, quantity cubed, should be a solution. T cubed over 27. But it's not the only solution. The solution of this IDP is not unique. Can you think of another solution? When does that right-hand side function equal 0? What value of y? Just one value of y equals 0. That's got to be an equilibrium solution of this differential equation. And it's a constant function, and it does satisfy the initial condition. And it's different from this function. There are two distinct solutions, in fact, of this equation. Distinct. These are different functions. They do cross each other at the origin. They touch at the origin. The graphs pass through each other, but they're not the same function. By the way, this is pretty standard notation here. This triple lines for an equal sign means that it's for all values of t. Sometimes verbally you say this function is identically 0, always equal to 0 no matter what t is. You don't have to put the 3 lines there. You could just put 2 and just emphasize this is true for all values of t. But I'm just informing you that whenever you see that kind of thing here, it means identically equal to 0, always equal to 0. So 2 solutions. 2, not 1. It's not unique. Is there a way to understand this geometrically? Why did this happen? Well, sort of. I'll tell you the sort of reason. It's not going to be completely satisfying. It doesn't really tell you for sure why there had to be 2 solutions. But it makes it a little bit more plausible. Geometrically, both of these functions indeed do follow the slope field of the right-hand side function. If we made the slope field for f of y equals y to the 2/3, which is an autonomous right-hand side, autonomous differential equation, slopes are going to be constant on horizontal lines. You've seen that before in the slope field. Here's what the picture looks like. And we see both functions in the picture. This blue function is phi of t equals t cubed over 27. T cubed over 27. Should have made that in blue. And the psi of t is identically equal to 0. Black line on the horizontal t-axis. Let me just double check something. I'm just wanting to make sure I said, okay, I did, no typos there. Okay. Let's make this blue. Equals t cubed over 27. They are different functions. They're only equal when t is 0. They're real close together when t is close to 0, but not equal to 0. But they only equal each other when t equals 0. And they do both follow the slope field, you might say. The horizontal line here, this equilibrium solution, follows the slope field because the slope field has horizontal lines when y is 0. And yeah, the blue curve seems to follow the slope field too. So this is an issue. You shouldn't want uniqueness to fail, right? If you're trying to use differential equations to make a prediction about the future, like sending a spaceship to Mars, and by the way, when you send spaceships to Mars, they do use differential equations to help them figure out how to get there. You wouldn't want different solutions. You wouldn't want the spacecraft for it to be unknown where it ends up, you know, either at Mars or somewhere else, off to Jupiter. You wouldn't want that. So this seems bad. Why did it happen? Again, intuitively, not a rigorous description here, while the right-hand side function, this function right there, is nice, it's continuous everywhere, it does fail to be differentiable at y equals 0. Maybe you knew that, maybe you didn't. So while it is nice, it is not sufficiently nice, not nice enough. Here's what its graph looks like. It's got a cusp right there. That point is a cusp, a corner, you might say. There's no tangent line at the origin for this graph. There's a tangent line everywhere else, but not at the origin. By the way, don't get confused here. This is going to come up a lot. It already has to some degree. The y-axis is vertical here. I didn't label it. This is y. While the y-axis is horizontal here. Don't be bothered by that. It's okay. It's okay to do that. This is a graph of the right-hand side function. I can make this graph without even thinking about differential equations at all. How is it relevant for differential equations? It helps you figure out the slope field and then draw solutions over here on the right. This is not a solution of the differential equation. Not a solution. These graphs are solutions. But this graph helps us understand the slope field. It helps us understand the slopes along horizontal lines. All right, here's our main existence and uniqueness theorem that we need for this course, in the one-dimensional case at least. I'm calling a local existence and uniqueness theorem because it's going to say solutions exist and are unique near the given value of t for the initial condition, near there, on some possibly very small interval. That's why it's local, nearby. There are global versions, though the hypotheses are more restrictive. You need to assume more things to guarantee solutions exist and are unique for all t. For all t means global over the entire real number line. Here it is. Suppose we've got a mixed right-hand side function. This will include the case where it just depends on t and just depends on y. So I'm going to write the general case here. Suppose that function is continuous and its partial derivative with respect to y is also continuous. These are both continuous functions of t and y. It's a multivariable calculus kind of thing here, both in the fact that these depend on two variables in general, and this partial derivative with respect to y is a multivariable calculus thing. It's not a big deal. I mean, when you differentiate this function with respect to y, you pretend that t is constant. Okay? So don't worry about it. It's not a real big deal. Being defined for both t and y means in general it's defined over the plane, the ty plane, the plane of the slope field, you could say. Again, we talked about drawing level curves and contour maps for these right-hand side functions in lecture 7a, and that helped us draw the slope field. We're going to assume here these are both continuous over some open rectangle R, which in a picture below I'm going to make it as a cursive R. R is a comma b cross c comma d. This cross means what's called a Cartesian product. It's just shorthand notation. These are not points, they are intervals, open intervals, from A to B and C to D. It's just shorthand notation to say it's the sum of all points t comma y, where t is strictly between A and B and y is strictly between C and D. I'll draw a little picture over here on the board. In the ty plane, which is where we draw the slope field and where we draw solutions. Let's pretend A is here and B is here and C is here and D is here. The rectangle that we're talking about is essentially the inside of this set here. So I'm making the boundary of the rectangle dashed to indicate the part inside is the only part that is technically included, not the boundary. These are not closed intervals here. They are open intervals. Could it be continuous over a closed rectangle with closed intervals there and there? It could be. But for the purposes of this theorem, it's best to assume an open rectangle. Let t0, y0 be a point in R. And here is the crux of the matter of why we assume it's an open rectangle, is because if we assume t0, y0 is a point in this rectangle, and it's an open rectangle, that's going to mean it's not on the boundary. Okay? And consider the initial value problem, dy dt equals f of t comma y of t0 equals y0. So no more y of a equals y0 like with the FTC. Y of t0 equals y0. t0 is our initial value of t that we're thinking about. Often t0 is 0. Then there exists a possibly very small number, epsilon, greater than 0. Epsilon is kind of the mathematician's favorite letter for small number. Actually, it doesn't have to be small. It could be big, but you usually intuitively think of it as small. So I'm saying possibly very small. It could be microscopic. It could be 10 to the negative a million power. That's how tiny it could be. Okay? Such that two things happen. There exists a function phi of t so that the initial condition is satisfied and the differential equation is satisfied. Phi prime of t equals f of t comma phi of t. Replace y with phi of t on both the left and right hand sides and simplify. As functions of t, these are going to be the same. For all values of t in some tiny interval, that tiny interval takes this form. Between t0 minus epsilon and t0 plus epsilon. So a solution exists. And again, epsilon could be microscopically small in general. Also, it's unique. If psi of t also satisfies the two conditions, the differential equation and the initial condition, then in fact, psi of t and phi of t must equal each other for all values of t in this, satisfying the same condition that t is between t0 minus epsilon and t0 plus epsilon. Okay? Existence is part A, uniqueness is part B. Proving this is very difficult, okay? Very, very high level math to prove this. If you look for an advanced ordinary differential equation book, you'll find it. You need some analysis, real analysis facts at your disposal, some pretty high level stuff, in fact, to be able to prove this. Here's a picture that shows the basic idea. Kind of similar to what's on the board, except I put t0 right there. And I made epsilon be, if this is t0 minus epsilon, this is t0, and this is t0 plus epsilon, then epsilon is this distance right here. That's epsilon right there. Kind of like a radius of a circle. This is a radius of an interval. The interval is centered on t0. Do I have to pick an interval centered on t0? Actually not, but this is good enough for the theorem to be a good theorem. I'm going to make some comments now. You need to understand this in more depth. And what are the consequences of this for this course? What are the main reasons we need to know this? Let's go back to the example. Returning to the autonomous example with the right-hand side function that's not differentiable at y equals 0, in other words, y to the 2/3. That was the one that had a graph like this with a cusp. It was not differentiable at just one point. If R, the rectangle, happens to intersect the horizontal t-axis, intersecting the horizontal t-axis where y is 0, then the local existence and uniqueness theorem from the previous page cannot be used. It does not apply for initial points on the t-axis, where y sub 0 is 0. T sub 0 could be anything, but y sub 0 is 0. this theorem does not apply. So redraw it here. If our rectangle happens to touch the t-axis, and we are talking about a point t0, 0 that's on the t-axis, the theorem does not apply. We can't use it, is what that means. So we have no guarantee of uniqueness. And we saw there's not a unique one when y0 is 0. Actually, we were talking about the origin then, but it actually will work when t0 is even non-zero here. You can't use the theorem. That doesn't guarantee that uniqueness fails. We know it does in this example, but just knowing that this rectangle contains the t-axis where y is 0 and where f of y is not differentiable is not enough to say for sure that uniqueness fails, though we happen to know by integration and by just inspection about the equilibrium solution that it does fail. On the other hand, even for this example, I'm still talking about the same example here, this one right there. If the rectangle does not intersect the t-axis, so that means this interval consists of all positive numbers, which would happen when c is positive, or it consists of all negative numbers, which will happen when d is negative. So the rectangle does not touch the t-axis like in my first picture, which I erased. Then you can apply the local existence and uniqueness theorem even with this right-hand side function, because the right-hand side function is continuous, and its derivative is continuous with respect to y. It's differentiable and continuous when y is non-zero. The cusp was only at one point, not the other points. And you can say existence and uniqueness are satisfied. The solutions do exist and are unique, locally speaking, for some small epsilon. As a side note, we saw in lecture 7a, there's a weaker version of the existence theorem that guarantees solutions exist when the right-hand side function is just continuous. That just continuity, even in this example here, the graph was continuous everywhere, is enough to guarantee existence, just not uniqueness. All right, take a breath. Here we go. Keep going here. Some more comments. A practical consequence of uniqueness. What's the practical consequence of existence? The practical consequence of existence is that you know you're studying something that exists. When you try to approximate the solution numerically, you know you are approximating something that exists. That's the practical consequence of existence. Okay? And that's a big deal. And there are some higher level topics in math, partial differential equations, where existence is not so obvious, or maybe even hasn't been proved, but people try to study it anyway. They might be studying nothing, something that doesn't exist, actually. What's a practical consequence of uniqueness? In the setting where these theorems can be used, like the FTC, when we have a pure antiderivative problem, or this more general theorem, where f of ty is continuous and the partial of f with respect to y is continuous on this rectangle. Distinct solution curves, in other words, the distinct solution functions, cannot touch each other. In other words, the graphs cannot intersect. The intersection of the two sets of graphs as sets of the two graphs as sets of points is empty. Keep in mind, though, that distinct solutions can be asymptotic to each other. They can often get arbitrarily close as t goes to plus or minus infinity. That will happen a lot, actually, in this course. You'll have solutions that, well, like an equilibrium solution and some other solution that approaches it as t goes to plus infinity in this case, and maybe another solution that approaches it as t goes to minus infinity. They get arbitrarily close together, but they do not touch each other at all when the existence and uniqueness theorem apply. And that's actually a pretty useful thing. And this is going to come up in my students' homework problems from Blanchard, Devaney, and Hall's book, is you'll see some problems where they assume you got certain solutions. Maybe you assume you got an equilibrium solution here, and maybe you assume you've got another equilibrium solution down here. You could say, by uniqueness, this graph has to go maybe like this for an autonomous equation. At least so, because the slope field would be constant along horizontal lines, it would not be able to go back up again. If it were a non-autonomous solution, a differential equation, then the solution could go back up again. But it would have to stay between these two equilibrium solutions for all values of t, if you know these are two solutions. Okay? And in fact, there's going to be an example here in a few minutes where it is a weird situation that is not really solvable, but you're going to be able to find equilibrium solutions. That's in a minute. Let's do something else at the moment. For example, consider the logistic model with harvesting. This model right here. Now, we've talked about the logistic model for population growth and decay, in fact, already. That's this part of the right-hand side function. There were equilibrium solutions at y equals 0 and y equals L. Solutions between 0 and L grow to L as t goes to infinity. Solutions above L decay to L as t goes to infinity. The long-term population prediction is y equals L. But now I'm adding this minus h term. And here's what it all looks like when you expand it. Representing harvesting. What's harvesting? Well, pretend the population is a population of fish. So harvesting is you're going fishing. And h is a constant. That would be the assumption that the fishing rate in thousands of fish per year, for example, is constant throughout the given year over time. Now, in reality, that doesn't typically happen. There are fishing seasons. But if we tried to model fishing seasons, we'd have to use something more complicated. This is a good initial approximation, perhaps. Solution formulas for this model are difficult to find. They actually are possible. You can separate variables and solve this, although having the arbitrary k, l, and h in there makes it hard. However, as long as the graph of the right-hand side function, f of y, this function right here, takes on both positive and negative values, this model will have equilibrium solutions, constant function solutions. The graph of the right-hand side function, if h is 0, is going to have intercepts. Now I'm labeling the horizontal axis y. That's not a mistake here. This is not going to be a slope field. It's not going to be solution. It's the graph of the right-hand side function, which helps you draw slope fields and solutions. But it in and of itself is not a solution. There's f of y when h equals 0. If I assume this number right here is L. L for limiting population carrying capacity. That's when h is 0. If I make h positive to represent some level of harvesting, I'm subtracting it, the graph's going to get translated downward. And it might look like this. When h is between 0 and some unknown positive number that's not too big, I could figure it out by figuring out the maximum height of this graph. That would be the value of h where the graph would just touch the axis. And then if h is large enough, it's going to go below. In the slide here, I'm talking about those situations. I hope you can see this actually with the camera. I'm not sure I drew it close enough to the screen here. In this kind of situation, right here, you got two equilibrium solutions because there's two intercepts here. Two equilibrium solutions. Now I'm drawing the phase plane here. Two horizontal lines that are solutions. Other solutions are going to look like this. Let you think about that. And if the initial conditions are between these two, you know it's got to be stuck between them for all t. This graph has got to be stuck between the two equilibrium solutions for all t. That's a guarantee. Some more comments. Just a couple more slides here, I think. These theorems and examples also have important implications for numerical methods like Euler's method. things can go wrong. They help you realize things can go wrong. Or maybe I should be better to say it helps you realize when things are wrong. That's a better way to say it. For example, you might be trying to approximate a solution of an IVP that blows up in finite time. In other words, has a vertical asymptote. Okay? There are plenty of examples like that. And so this will necessarily be a bad approximation. There's no way Euler's method is going to give you a graph that blows up in finite time that has a vertical asymptote. That won't happen with Euler's method. There's another example. Sometimes numerical methods can produce wild results, crazy looking. Knowing the theory can help you realize that such results might be fictitious, false, incorrect. Consider this differential equation. dy to t equals f of ty is e to the t times sine of y, a mixed problem. It is separable. We could try to divide both sides by sine of y and multiply both sides by dt and integrate to see if we could solve for y. A little bit of thought would reveal that would not be pleasant, but maybe doable in some sense. However, even though it's complicated and non-autonomous, it's got equilibrium solutions that are pretty easy to find. Y equals n pi. For n is 0, plus or minus 1, plus or minus 2, etc. Because that's where the sine function equals 0. We've got a sine of y there. Those horizontal lines are all equilibrium solutions. What happens when you try to apply Euler's method to this? And I picked, as the textbook does, delta t to be 0.05 and n to be 120. So we are approximating over the interval from 0 to 6, 6 being 0.05 times 120. You get the following graph, which cannot possibly be accurate because we know where the equilibrium solutions are. Here's what the graph looks like. We know there are equilibrium solutions at 0, at pi, and at 2 pi. And it does look like this solution is approaching pi at first, but then all of a sudden it goes wild. And that can't be the case, because you can't cross those equilibrium solutions. So the uniqueness part of the theorem is saying that's got to be wrong. Why did it happen? Intuitively, it's because e to the t, that part grows so fast as t increases, it causes this kind of crazy stuff to happen. I don't know that I can say much more about it than that. I mean, that makes some intuitive sense. All right, here's our last slide for Lecture A. An introduction to phase lines for autonomous ODEs. Lecture 9A is going to mostly be about phase lines and more examples. In fact, so this is a pretty theoretical lecture. Lecture 9A, we're going to do a lot of examples. Recall that the slope field of an autonomous ODE, dy dt equals f of y, right-hand side just depends on y, has constant slopes along any given horizontal line. My students, if I asked you that on a test, why does that happen? Could you explain it? Do you understand it? It's because of how we make slope fields. The right-hand side depends just on y. In a ty plane, you'd make slope marks, little mini tangent lines, with slope equal to the y coordinate of the given point. And along horizontal lines, the y coordinates are constant. So you get a bunch of line segments with the same slope. And that ends up meaning, as another practical implication, is that many solutions are horizontal translations of each other. Like solutions between these equilibrium solutions are horizontal translations of each other. Other solutions are horizontal translations of each other. It's another thing it implies. But yeah, autonomous equations have solutions which can't oscillate. They got to be constant, or always increasing, or always decreasing. But because of that, the slope field really contains a lot of redundant information. I mean, it's constant along horizontal lines. I can effectively just focus on one solution in each one of these regimes for y and what its behavior to say what all the other solutions do. So the phase line takes the slope field and solutions in the slope field, and the information that's inherent is the function constant, increasing or decreasing, and compresses it onto just the vertical y-axis. Consider this example. F of y is 3y minus y squared. Factor of the y, you can also write that as y times 3 minus y. Two equilibrium solutions at y equals 0 and y equals 3. Here's what the slope field looks like, kind of similar to this one over here. And how do we compress this information onto the y-axis? Like this. This blue arrow is just an arrow to go from here to here. To draw a phase line, you draw a vertical line to match this vertical line. You could draw it horizontal, but we want to remember it's related to the slope field. Equilibrium solutions become equilibrium points. What are these arrows? These arrows indicate the direction of solutions in the different regimes, the different intervals of y, where you've got solutions that are horizontal translations of each other. So solutions with initial conditions above 3 are always decreasing, like you see here. And actually, this one actually does have a vertical asymptote over here, though I won't explain why. So we draw an arrow going down, solutions decrease. In here, between y equals 0 and y equals 3, solutions are increasing. Draw an upward pointing arrow. And down here, when y is negative, solutions decrease, draw a downward pointing arrow. This function actually has a vertical asymptote. Some of these solutions blow up in finite time, and so we'd have to be wary of that with Euler's method. Okay? When the arrows point toward an equilibrium point, which again corresponds to an equilibrium solution, we call such a point a sink. It's kind of like water going down a sink. And what's such a point? An equilibrium point that corresponds to an equilibrium solution has arrows that, well, nearby at least go away from it. We call it a source. It's like water flowing away from the point. And in fact, this is the last thing we'll do. We'll look at Mathematica briefly here. Discard my annotations. It's best to try to visualize the slope field as an animation. I don't have the time to talk about all the Mathematica code here in detail. My students, I will give you an opportunities to practice this code. This enters the right-hand side function, for our example. This is the use of d-solved value to solve the differential equation y dy dt equals f of y, but Mathematica needs the t's in there. That's just the way Mathematica works. For a generic initial condition, y of 0 equals y 0. Right there with the subscript, y sub 0 by hand. Solve for y of t with respect to t. It gives you a little warning here because it says inverse functions are being used, but you can copy and paste. This does work. That down here. There's your generic solution, phi sub y0 of t. You need underscores when you define functions again. Vector plot will plot the slope field. Plot will plot solution curves and show, as you see here, will combine the different graphics objects. So I'm combining this vector plot right here, this plot right here, this plot right here, this plot right here. That graph, these solution functions with different certain thickness and colored red, and this vector style is blue, the slope field is going to be blue, with a certain plot range, etc., and it gives you this graph that you can already see a little bit of right there. This will plot the phase line. I'm not going to get into details. We can put them together in a grid, an overall picture like this. And then, in general, we can animate them. Manipulate is one Mathematica function that will make animations. I'm not going to explain this over the lecture here because we're so long on time. But just to see what the result is here, here's the animation of the phase line. The red points, the red dots, are the equilibrium points. The green dots are not equilibrium points. They are y values of solutions at certain times. You want to imagine the points, and I could have drawn more than just these 3 points that you see. I could have drawn a bunch of them. You want to imagine the points up here approach 3 as t goes to infinity, and the point down there goes away from 0 as t goes to infinity. This point also goes away from 0. You want to imagine phase lines being animated even when you draw them as static diagrams. Okay? And it corresponds to the solutions either decreasing, increasing, or decreasing over there. All right, and that's the end of lecture 8A. Thanks for watching.